Hello, everyone, and welcome to the Geek Nighter podcast. I am your host, Kaival Yapte, and I am back with another interesting episode. Today, we are going to discuss something which is one of my personal favorites that is database internals, how databases traditionally and in modern databases, how internal things are implemented and how they work and why they work the way they do. And to understand all these complex ideas and techniques and strategies, I have someone who has vast experience in the world of databases. So, with this, let's welcome Frank. Frank is working at Yugabyte DB, and his experience in world of databases is more than 20 years, and so I would you know ask him to introduce himself even further in detail and his journey into the databases. So, Frank, welcome to the podcast. Thanks a lot for joining. I'm really excited to learn from you and learn more about the database internals.
Hi, thank you very much. I'm really happy to be there and yeah, talking about databases
Awesome.
and distributed and the future of databases. Yeah.
Yeah. So yeah, let's start with a little bit of introduction for our viewers about your journey into software engineering, database world. What have you been currently doing? Let's go through that.
Yeah. So I've been always working with databases. I started at school and then on DB2 quickly on Oracle, so the commercial databases at that time. A lot of years with Oracle from the development side and the operation side, and mostly as a consultant, so going at customers, and that was really nice to meet people, but also to meet different kind of workloads and users. I've started to look at open source databases at Postgres mainly,
Hmm.
still doing consulting. And then 2 years ago, I changed a lot of things, not being a consultant, but being a developer advocate. And on open source distributed database, Yugabyte. So was apparently a big change, but finally I'm doing the same kind of thing, listening to what user needs, helping them, and getting feedback also to discuss with the engineers.
Awesome. Yeah, that's a lot of experience, and talking to customers and users of the database gives you like a different perspective from a different side. So, yes, I'm really excited. Let's get a little deep into the topic. So, let's discuss the agenda first. So, we are going to discuss about the types of databases we are going to talk about, and then how they internally work, how they internally implement some of the techniques and strategies, and some of the internal data structures that are used primarily in the modern databases, and also traditionally how it has been used. uh, Before we do that, I have a personal interest into learning more and more about internals of databases. So we did a podcast on Cassandra, Cockroach DB, a little bit on Yugabyte, and also the search databases side of the world. uh, and I get this question from developers and also architects, that why is it important to learn or to know about the internals of databases? I just have to write code and database should work, right? So I wanted to ask you, how does it help as a developer or as an architect to know more about database internals?
Yeah, I'm convinced it helped, and also from my experience working both on the development side, so data modeling, development, and on operations side, where you really look at the performance from CPU I/O point of view. I'm
Yeah.
convinced that you need to understand how it works, even if there are several layers of abstraction. For example, SQL gives you this logical physical independence, so you
Yeah.
can query the database from a logical point of view.
Mm.
But if you don't understand what happens behind, then you may have performance, scalability, or even consistency problems.
Mm.
So for me it's really interesting, maybe not to know everything, but at least the patterns and what is behind. For example, I've been discussing with developers who had no idea that querying one colon or all colon may be the same, or that or the opposite. So knowing how it is stored, how it is retrieved, and the complexity of it.
Yeah.
And also something I see, people who don't know sometimes guess. They think their query is fast because it is a small query, and they do not realize that their small query is reading the whole database.
Yeah.
Or the opposite, they think that having many joins will take long, where maybe not, because a lot of things are. So yeah, that's something I always tried, and that's also why I try to share a lot with people, developers and operations, really understand the complexity of it, and avoiding any guesses, because IT is kind of a science. You have
Yeah.
facts. That there is no random, there is no magic.
Yeah, yeah, yeah. Absolutely. And I completely agree. So I also have personal interest, but I also agree that, it helps if you know the internal workings, how data modeling is done ideally. You cannot implement, let's say, SQL data modeling concepts into NoSQL databases or something like that. And it might have some trade-offs, and those decisions become critical on the type of application you are building, right? If it's like a simple application, maybe you won't notice any difference. Maybe it will just work. But if it's really mission critical application with a lot of data coming in, where performance, low latency is like really critical, I think it can make a huge difference. So I totally agree with that. With this, let's discuss the types of databases at a high level that we are going to talk today.
Yeah. So from my experience, as I've been working a lot with what is called now converged databases, but
Hmm.
like Oracle, for example, where I've seen all kind of workloads on the same database.
Yeah.
OLTP, data warehouses, time series, even text search. There are many things that can be done on a RDBMS, on a SQL database, because of the many features.
Yeah.
But still, even if you use the same database, you need to understand the workload, because you will not set up in the same, you will not use it in the same way. So basically, what I've always seen, and 20 years ago, like today, first you have two kind of workloads: OLTP and analytics. We were calling that OLTP and DSS, decision support system, at that time, or data warehouses, or all that. But
Hmm.
basically, OLTP, you mostly have a key and get a record. So those are also called system of records.
Yeah.
And analytics, you probably don't need the whole record, a few columns of them, and but many rows. And
Hmm.
there are also other databases optimized for that with columnar storage.
Yeah. Okay.
Those are the main thing. And then, of course, the needs about consistency, about distribution, will depend on the application. But the most important is, are you more reading a few records, or are you more reading, aggregating a lot of rows on different things? And I'm saying reading, but there are also write workloads. Usually databases ingest data and then you query it. And
Yeah.
this ingestion can be a bottleneck or not. If you load a data warehouse during the night, probably the ingestion is not a bottleneck. If you are in time series and have to ingest data from sensors, then you optimize for that.
Absolutely. And at a high level, so I think you briefly said about monolithic databases, which are doing everything that you need, like OLTP, analytics, and all that. And then there is the distributed side of the world, whereas it comes NoSQL databases and distributed SQL. So what is the difference? And why did we need to distribute monolithic databases?
Yeah, and that's a question, because there are some there are also some facts and something that people guessed. People
Mm.
always think they need to scale out,
Yeah.
especially and when they see the technologies that are built by Google, Amazon, they think they need it, but probably they don't have the same business.
Yeah.
And the need to scale out has also, for example, a few years ago, let's say more than 10 years ago, we had very limited single boxes in terms of CPU and memory. And
Mm.
then you needed to scale out if you wanted more power. Today, you can run a lot on one single server. But then came the cloud, where maybe it is cheaper to have multiple instances rather than one. So the reasons to scale out are a bit different. But when I discuss distributed databases, I see that people think performance first. And that's probably from what you were saying. If they don't know how it works, then they think they need more power, more resources. Where for me, the first reason is high availability. You
Mm.
distribute to be able to handle failure. So you distribute and you replicate. And this is really where the NoSQL databases came. This needs to have data in more than one place because
Mm.
your users are not in one place and because you are going to a cloud where everything can fail,
Yeah.
and then you need to replicate on that. But NoSQL databases, to be able to do that at that time, had to give up on many SQL features. So the main feature was distribution, and then everything else had to be done in the application.
Yeah, yeah, that makes sense. And that's a good point. I mean, it's not about scale, but it's, I think, primarily about the availability of data. And so you can be more resilient. And, because the type of applications that we are currently building is way different than we used to build, let's say 20 years ago. And the availability of the hardware and the type of the workloads that we are serving are also completely different. So yes, I think it makes sense. You covered a little bit on NoSQL as well, but where does distributed SQL database come into picture?
Yeah. So in my experience, I always followed the new databases. And when I've seen NoSQL databases, of course, I was interested by that. But with a long experience on SQL, giving up on many critical features like just consistency was
Yeah,
for me kind of difficult, except for specific use cases. I totally understand, for example, that Amazon puts the shopping cart on DynamoDB
yeah,
because that's really a use case where you don't need consistency with other users. You have each user has his shopping cart, so that's perfect.
yeah,
But when you start to do LTP, you need you need consistency. You need also to be able to access from different use cases. You ingest data, but then you
yeah,
have marketing with specific queries, and you have uh, many different use cases, means many different indexes that must be consistent. And in NoSQL databases, usually you access by the primary key and you have secondary indexes, but they are eventually consistent. So that was one thing. And also the reason distributed SQL databases started with Google Spanner. And Google really explained why they did that. They had no SQL databases to scale at Google scale,
yeah.
like big tables, and but they realized that it's easy to start because the API is quite simple, but it's quite difficult to evolve the application.
Mm,
Because what the database doesn't provide, all the SQL feature, you have to do it in the application. And do it is not only code, but also testing.
yeah,
What I love with RDBMS, with SQL databases, is that if something works in a unit test, you know that it will work even with multiple users in race condition,
yeah.
because the race condition has been tested by the database. The
Mm,
fact that you do not corrupt data if multiple people try to write on the same thing.
yeah.
In a NoSQL database, you have to handle that in the code and in your test. And
Yes.
that's not easy. I'm not sure everyone has regression tests that will test all race conditions that will happen at production in production at some time.
Yeah. Absolutely. And that's a great point. So the simplicity that like traditional SQL databases provide you is like cannot be compared with the modern databases, and a lot of that complexity is shifted towards the application side, and the application developer needs to handle all those edge cases, race conditions, and it's not only about implementing those, but it's also about maintaining those without breaking them at any point in time. And writing those race condition test cases is really difficult, even like from my experience. I faced some of the issues around consistency and race conditions, updating the database with some stale data and all that. So yes, it is definitely more challenging. And so I think understanding the context of your application, the type of workload that you're serving, is really critical before making any decision. Because if let's say you are using AWS, that doesn't mean that you can just go and use Amazon DynamoDB because it's available. It's easy to use, and I think one wouldn't understand the difference or the problems if they are just starting out. But once the application scales, let's say 2 or 3 years down the line, they might see some problems in maintaining such a system. So I think, yeah, again, tying it back with the first point that we made, that it is important to understand the context and also attach it with the internals, how things work internally. Um, right, with this, let's talk a little bit on the internals, right, and how internals are typically implemented. So when I see like a block diagram of a database, let's say a SQL database, what is happening internally, what kind of data structures are used, and why they are used in such a way.
Yeah, the big difference before working on distributed databases, I've seen mostly BTrees for indexes.
Hmm.
And even because I've been working mostly on Oracle and Postgres, um, something that is very different with Oracle and Postgres is that the table itself has no order. When you insert data in Postgres or Oracle, it goes anywhere physically.
Yeah.
And then you have indexes, and the primary key index is just an index like other indexes. And that's something different, for example, from MySQL, from SQL Server by default, where the table is stored in the primary index.
Hmm.
Of course, some databases can do both. For example, in SQL Server, the default is this index organized one, and you can also have heap tables. In Oracle, the default is heap tables, and you can have index organized tables. Postgres, you don't have the choice, so there are those choices. Usually, people use the default. A database is already complex, and as we mentioned, some people do not want to know how it works internally, so you will not look at the different possibilities. But that's a big difference I've seen. First, heap table versus BTrees.
Hmm.
Heap tables versus all the tables stored in a B-tree, the primary key. But then B-tree is always there in monolithic databases. Basically, a B-tree is a sorted structure that is maintained as a tree. So when you query, you have to go to the root and then the branch, depending on the range of data, and then a leaf. And the big advantage of it is that you know exactly how many blocks you have to read to get to a row.
Yeah.
Uh, the drawback of the B-tree is when you have to update it because you have new rows or you update an index value.
Yeah.
When you have to update it, it must be updated in place within a block,
Yeah.
and then maybe have some split of the block in the tree. And this is okay in a monolithic database because in a monolithic database, you do not directly write to the storage. You write in memory, in shared buffers, and then it's possible to update in place a few blocks. and those buffers are written later to the disks. And that's okay, especially with modern hardware where you can have a lot of memory and where maybe not your index will stay in memory, but at least the first branch and the first root and branches.
Yeah.
But this is where you have a problem when you start to build a distributed database, because this is all about updating blocks. And if you have multiple nodes who need to read or update a block, then they have to share the block. It's easy to share a block in memory with the processes.
Yeah.
But if you want to share among multiple nodes, you have to ship it. And that is difficult. Some databases do that. For example, Oracle RAC can open one database from multiple servers, and they ship the current block. So one node has to update it. It takes the current version of it. Another node will ask for it. But they can do that only with specific network and interconnect network with very low latency. Of course, you cannot ship blocks between availability zones or regions.
Yeah.
And in my opinion, this is where databases needed something else than BTrees, a structure where you do not work with block, where you just work with values, keys and values. And this started with NoSQL databases like Cassandra, HBase, and this is where the LSM trees are coming. And just about the name, B-tree is a balanced tree, so a tree that is always balanced, but this balancing requires updating the blocks and splitting the blocks. LSM tree is a log structure merge tree. So log means that you always happen. So you can imagine the fast ingest that you have from that. Any insert, but any update will be an append of the new value, the new version of the column. So that's quite fast to ingest. Then the challenge is to query it, because if you keep it as a log structure, then it will grow. And when you have to query something, you will have to rebuild the history of the row. And this is where the merge comes there. At some point, this log must be merged and compressed to be easier to query.
Yeah, that makes sense. And I think you mentioned B trees are like balanced trees. I've also seen this confusion since we just talk about B trees. Some people think it's binary trees, but it's not. It's more balanced trees. And I think you mentioned the drawback or the challenges that we might face if we use B trees for high workloads where data is coming in really fast. And I think just to validate the understanding there, uh, the challenge is that you have to read the entire block and then split it and store it again after updating the value. And for the other use case, for the LSM, it's just appending, and then the update is actually taking place after the fact, right? So is that the like the separation of the operations that we are performing? Is it making LSM a little bit better when it comes to high write throughput, for example?
Yeah, first for high write throughput, but also when you want to distribute, because it's easier to distribute a log. You just send the new version on all nodes. Of course, we may talk later about the consensus about it to keep it consistent, but you just distribute the new versions.
Yeah.
And that's easier than with B-tree. You have blocks that are a single point of truth, and a block has many rows. So even if two sessions are not updating the same row, they have to share the block.
Yeah. So
And
there's
sharing and writing, then this doesn't really scale. So basically, B-trees are very good, but there is a point where they cannot scale out, except if you really split the database before, like the sharded database used mostly for data warehouse, where you split the database and then you have kind of multiple monolithic databases, and they can use B-trees. I think that even some NoSQL databases use BTrees. For example, DynamoDB use BTrees, but it is partitioned at the beginning. You can access it only by the key for the consistent reads and writes, and then you have small monoliths that are distributed.
Yeah.
But yeah, LSM also makes many operation easier from what I've seen. For example, when you have only append in files, so maybe we'll go into the detail or LSM, the memory part and the files. But when you only append, then you can do many things that are difficult with a database that is changed in place. For example, I've seen a lot of incremental backups on terabyte databases. With BTrees, with monolithic databases, you usually have to read all the database to see what has been changed. With LSM, an incremental backup is just a snapshot of the current LSM tree, and then the new incrementals will be abandoned. So it has many advantages, but it requires optimization to read it, because at some point, when you read it, you have to read at multiple places. Basically, BitTree do more work, but build and store the database ready to be queried.
Yeah.
LSM trees has something else to do in the background.
Okay. So is it okay to say that, for a B-tree based database, when we do the write, all the operations are happening right there, so the data is queryable, and for LSM based databases, it's just writes and then does the other operations for making it queryable asynchronously, and then it will be queried. So it has to do a little bit more work while reading the data as compared to writing. Whereas for B-trees, more work is done while writing the data, and reading is simple. Is that good enough?
I can go a bit into the detail of the implementation, for example, that we have in Yugabyte. So the LSM tree has multiple levels. The first one is memory, because you want to ingest data, and that goes into memory. So for example, each table or index in Yugabyte is a LSM tree with a memory table. This is based on RocksDB. This is how RocksDB works. So it goes into memory. So you insert data, you can ingest very quickly. It's just put in memory in a sorted structure. And when you query it, you query from a sorted structure in memory. That works. But at some point, you cannot put everything in memory. So by default, I think in Yugabyte, we set it to 128 megabytes.
Okay.
At some point, when this memory is full, it is flushed to a file. So that's kind of easy, flushing the memory to a file. It was sorted in memory, so it is sorted in a file. This is called a SST file, a sorted sequence structure table, and it goes to a file. And then new data ingest go to memory. And by ingest, it can be insert, or it can be also an update, the new version, or a delete that says this row is deleted. So then when people query it, they have to look at the memory and the file. So 2 places. And if you continue like that, you will flush. And then at some point, a query will have to look at many places, which would not be possible with mechanical disks, given the latency, which is possible with SSD, where the read latency is much lower. But at some point, you have to do something, because you will have too many files. And also, you don't need all information in them, because you have all versions there. It is important to keep all versions for the past minutes or hours, because for read consistency, you may have to see an intermediate version. But after a while, you don't need those intermediate versions. So the idea is that a background process will remove the intermediate version that we don't need and merge the files. So if you have 5 sorted files, you have many things to remove from them, and those can be merged into one, maybe bigger file.
Yeah.
And then the reads have only one file. So
Okay.
this is background. This looks like, you know, Postgres, the big problem in Postgres is the vacuum. So this looks like vacuum because it's kind of garbage collection, but
Yeah.
it is at a lower level. You don't need to lock anything. You don't compete with active DML. This is just in the background taking files, and those files, those SST files, are immutable. It is written either by a flush or by a merge, but once the file is written, it doesn't change.
Yeah.
So you have your incremental backup,
Yeah.
and you also reduce a lot the risk of storage corruption because you are not rewriting into it.
Yeah.
Once it is written, the probability that something will corrupt it, something is very low because nothing is writing to it.
Yeah. Yeah. Absolutely. I think it makes sense. And as you said, for LSM, there are like multiple layers of, where we can work, and, and then later asynchronously, some of the threads work and then try to merge these and compact and, delete some of the old ones. And I was reading some blogs, I think by Microsoft Research, and they mentioned like it is a trade-off between, what you want to do. Like sometimes it happens that the writes are too fast that there's no bandwidth or no space left for the merging task, so it makes the size grow and grow, and eventually it becomes a trade-off, and you will see a spike in writes as well. And sometimes it's the other way around, where the merging task takes a lot of time, where the write itself is impacted. So it was a good talk. I'll share it in this video. Thanks a lot for watching the part 1 of this episode. If you liked it, please don't forget to hit the like button, share it with your network, and subscribe to the channel. See you in the part 2. Thank you.